as I was just saying, we're going to take a PDE and solve that thing. And the approach we're going to use is called separation of variables. So the idea behind separation of variables is if the solution of a PDE depends on n independent variables. For example, what we're going to see today is a PDE that has two independent variables, x and t. So we're going to separate that PDE in two variables into two ODEs that have a parameter in them. So really it's two families of ODEs. And then we'll rely on our knowledge of how to solve ODEs, like from your first ODE course, like Math 285, and use the solutions of those ODEs to obtain a solution of the original PDE. Now, this is a very nice technique for the limited category of PDEs for which it actually works. For one thing, the PDEs must be linear. Also, the boundary conditions have to be linear and homogeneous, meaning, like for example, if it's a type 1 or Dirichlet boundary condition, where the value of the solution u is set on the boundary, those boundary values must be 0. Or if it's Neumann boundary conditions, type 3, where like du dx is equal to something, that value must also be 0. I wouldn't say it's an absolute requirement that the PDE boundary conditions have constant coefficients, but generally that's when this is applied. Only in certain very special cases outside of that is separation of variables useful. So it is very limited, but we'll do what we can. So what we do is we're going to write our solution u of xt as an infinite series. So it's an infinite linear combination of solutions of a PDE, where each one of these functions, u sub n of xt, notice so capital Un, satisfies the PDE and the boundary conditions, and these coefficients, a sub n, are chosen so that the entire sum will also satisfy the initial condition. So the initial condition does not come into play until the very end. Now, I got a notification that I'm still having network trouble, but it looks like scrolling is still possible. If something goes screwy with scrolling, you may have to point it out, those of you who are here in the room. Now, so if we can find these for each value of n, then there's only the initial condition left. So how do we get these that satisfy the PDE and the boundary conditions? So what we do is we assume that each one of these functions has this form, a function of x times a function of t. And we're going to obtain each one of these by solving an ODE. So we're just trying to take this more complicated differential equation and break it down into simpler ones. So what we do is, since this function needs to satisfy the PDE, what we'll do, or we're basically going to substitute it in the PDE and figure out what equations they satisfy. So here's a specific PDE we'll work with. So it's going to be the heat equation. So ut is a coefficient alpha squared times uxx. Our domain is the interval in space is the interval 0, 1. Oh, sure enough, it is not scrolling. Okay, there it is. Dang it. Technology hates me all of a sudden. Okay, so this is a PDE. Here's our spatial domain. Here's our initial condition. So u of at time 0, the solution is equal to some unspecified function phi of x. Now, so this function is going to be given. We're not dealing with a particular phi of x now. And here are boundary conditions. These are type 1 or Dirichlet boundary conditions, where u is set equal to 0 at the endpoints in space, x equals 0, x equals 1. All right, so PDE, initial conditions, boundary conditions. Sometimes I have to watch this as I go and not continue until what's on my screen is on your screen. Or we might have to unshare, reshare. Yeah, I've already scrolled a whole half page, and you're not seeing any of it. Okay. All right, I'm gonna unshare, reshare. Usually when it tells us to share, sometimes it'll be like, no, I'm not going to. I don't feel like it. And I just have to try again. And show it, and I'm like, oh, you're serious. Yeah, because I've unshared and it hasn't taken this down. All right, I'm going to try leaving the meeting without ending it and coming back. Now it's not wanting to let me back in. This is very much not my day. Okay. I've jumped off Wi-Fi to use a hotspot. Well, that's good to know. Okay. Okay. Okay, so we assume a solution of this form, function of x times a function of t. We substitute it into the PDE. So this is still a PDE. This is qt, and over here is uxx. So for du dt, we're only differentiating the t part, because the x part is considered a constant in that case. Then we have alpha squared, and then here we're only differentiating the x part twice. So this is uxx. Now, we rearrange this by dividing by x and by t. And now we have, and then the alpha squared I'll lump in with the t's, just for convenience. So now what we have here is this expression is a function of only t on the left side. Right side is a function of only x. Now, x and t are independent variables. The only way that a function of t can equal a function of x everywhere is for both of them to be equal to a constant. So, what I do is say that this is equal to a constant that I'll call k. So then I have two equations here, x double prime over xn double prime over xn must equal to k, which gives me this ODE. And then similarly, this fraction equal to k, rearranging, gives me this ODE. Now, this one, the ODE in X has to satisfy the boundary conditions. So it's equal to 0 at both endpoints. X equals 0, X equals 1. Now, we don't know anything about the constant k at this point. We just know it's some constant. But it turns out there are certain values of k that are not possible. So we're going to look at 3 cases. First is we assume a k equals 0. So in that case, we go back up to the ODE, that just says that xn double prime is 0. When a second derivative is 0, then the function must be a linear function. So something of this form. But this has to satisfy the boundary conditions. The only way a linear function can satisfy these boundary conditions, we're specifying 2 points on a line. If a line hits the x-axis twice, it actually must be 0 everywhere. And that's what this algebra shows. That if I plug in x equals 0 and x equals 1 and set this equal to 0, this is what I get. So the b has to be 0. I substitute that in here. So the a must be 0. That means this function must be 0 entirely. And that's not going to help us. We need non-trivial solutions, because whatever solutions we have, we're going to multiply them by constants and add them up. So if we get something at 0, it makes no contribution. So now we know that k must at least be non-zero. Any questions so far? Next scenario, k is positive. So what happens here is, if we have this ODE when k is positive, then there are 2 possibilities for a solution. This is something you learn about in Math 285 when you're solving second order ODEs. That the solution must be a linear combination of this kind of exponential, so e to the square root of kx, or e to the minus square root of kx. And then these constants, a and b, are chosen to satisfy the boundary conditions. So once again, we plug in x equals 0, and set it equal to 0. That's this equation. Then we set x equal to 1, and set the result equal to 0. That gives us this equation. Now, it can be shown from linear algebra that this system of equations, when k is positive, has a unique solution, and it's only, once again, the trivial solution. A and b must be 0. So it's because of the boundary conditions that this constant k cannot be 0, cannot be positive. So the only option left is that it must be negative. Now, in that case, from solving second order ODEs, the solution has this form. So it's equal to sine, and here we have square root of minus k. I want to emphasize that only the minus k is under a square root sign, the x is not. But this notation is kind of cumbersome, as you can see here. And since we know k is negative, I'm going to write k in this form, minus lambda squared. So that makes clear that k is supposed to be a negative number. So in that case, I can write my solution this way. Constant times sine of lambda x plus another constant cosine of lambda x. So in this situation, it turns out we can find a non-trivial solution. But we still have to make sure that it satisfies the boundary conditions. Oh, okay. That's something I will enforce later. But for now, we're going to work with this. But we don't know anything about lambda except it's negative. We'll find out what values of lambda have to be soon enough. Boundary conditions will also determine the values of a and bn. Now we turn to the other ODE, the one for time. So the ODE for time was originally this. But now we're writing k as minus lambda squared. So instead of writing it like this, let's replace k with minus lambda squared. Then this is what I get. Now this is a first order ODE, and this is the general solution. So it's an exponential. So we have e to the minus this constant times t. Now, keep in mind, for our un of xt, we're going to multiply tn by xn, where these constants, an, bn, cn, have yet to be determined. But really, since there's no reason not to set cn equal to 1, just for convenience, because we still have these two coefficients that have to be determined. So what we have here is this function satisfies the PDE. So any function of this form. Any questions up to this point? Now, I've taken care of a PDE, still have to deal with boundary conditions and then the initial conditions. So we go ahead and substitute x equals 0 and x equals 1 in here. So we substitute x equals 0, this is what we get. Now, an exponential of any kind can never be 0. That means that bn must be 0. And then we set it x equal 1, and this is what we get. Again, this part can never be 0. bn is known to be 0. So because this is gone, and this is not 0, this part has to be 0. So to ensure that happens, and this has to be true regardless of what an is, because an is set by the initial conditions. Sine of lambda must be 0. And this is where you fall back on your trick. When is sine of an angle equal to 0?
Pi times n.
What?
Pi times n.
Yeah, integer multiple of pi. So that's what we require here. So lambda must be an integer multiple of pi. So now we can take it into account, and I'll fill in lambda equal n pi up here. So now our solution has this form. So this satisfies both the PDE and the boundary conditions. And this is true for any integer n, 1, 2, and so on. Now, I want to explain why we only require positive integers, because this is certainly true whether n is a positive integer, or negative, or 0. We certainly don't need n equals 0 because sine of 0 is 0. That would be a trivial solution again. If n is negative, we have this to keep in mind. Because sine is an odd function, sine of minus n pi x is just the negative of sine n pi x. In other words, these two are not linearly independent, so there's no need to consider them. Like they would be redundant. So now it's possible to describe our solution as an infinite linear combination of these solutions. So we've taken care of the PDE and boundary conditions. All that's left is the initial condition. So we're assuming our solution now has this form, and all I'm doing is just summing all of these up and going from 1 to infinity. Now, the initial condition is enforced when t equals 0. So I just set t equals 0 in here. And so the exponential will go away because I have e to the 0, which is 1. And then I set this equal to my initial condition, whatever that is. So the constants an have to satisfy this. Then how are we going to do that? Okay, here's what we're going to use to help us get these coefficients. Notice I have in here sine n pi x, where n is a positive integer. So this integral, if I take sine n pi x and multiply it by sine m pi x, where I assume m is not equal to n, and I just go ahead and work out the integral. Here I use a trig identity that's called a product to sum formula that gives me this. So because this product is written, I don't have any convenient integration rule for that. But by writing this product of sines as a difference of cosines, these I can integrate. So using a U substitution, this is what you get. M and n are positive integers and not equal, so I don't have to worry about dividing by 0. But if I plug in x equal 1, either way I'm taking sine of an integer multiple of pi, which is 0. Then plug in x equals 0, I'll have sine of 0. Again, 0. The whole thing is 0. On the other hand, if m equals n, then I have sine squared of n pi x, because I have 2 of these now. Now this I can handle differently. I use a half-angle formula to rewrite sine squared. So now this can be integrated. And when I work it out by plugging in the limits, I get 1/2. So this integral is 0 if m and n are not equal, 1/2 if they are equal. Now I can show you how it's going to help us. Another way of putting this is these functions, sine of n pi x, are orthogonal on the interval 0 to 1. You would have seen the term orthogonality before in calculus 3. Suppose you take two vectors and you take their dot product and you get 0. Then we say the vectors are orthogonal. So the term is a similar meaning for functions. Now, what are you doing? You're because in a dot product, you're multiplying corresponding components of the vectors and then adding all those products up. Here it's a similar idea. We're multiplying corresponding components of these functions. In other words, value at the same x, and then, in a sense, adding them up, because what is an integral? It's a limit of a Riemann sum. So this is like an infinite version of the dot product of vectors. If this integral, this dot product, turns out to be 0, then we say they're orthogonal. And orthogonal sets of functions are very nice to have because they can solve a problem that we currently have. We're trying to find these constants so that our proposed solution of the PDE satisfies the initial conditions. So here's what I do. If I go back to where I was, I have my initial condition equal to this sum. People need to stop emailing me. Okay. So what I do is, I take this equation and I multiply both sides of it by sine m pi x, where m is an integer. And then I integrate both sides from 0 to 1. That's what gives me this. Now, I can pull the summation out of the integral, and this constant an I pull out of the integral. What's left? The integral I was dealing with before. And we know from above, this is equal to 0, unless n is equal to m. So all of these terms drop out, except for the case of n equal m, which is 1/2 in that case. So this integral turns out to be 1/2 am. That's what I need, because I'm trying to find values of these coefficients. So now I have that. So now my solution as given by this series, which I had a little while ago, but now I know what these are to satisfy the initial condition. An is equal to this. So I should mention that this series, so without the exponential, which is therefore equal to 5x, is called a Fourier sine series. We'll be seeing a lot of that. Also Fourier cosine series. So when your PDE has Dirichlet or type 1 boundary conditions, your solution has the form of a Fourier sine series. If they're type 3 or Neumann boundary conditions, then it's a Fourier cosine series. If it's type 2, it depends. Okay. Or if you have different boundary conditions at each end, that could affect what kind of series it is. Now, if this function phi is continuous and it's equal to 0 at the boundary points, then this series will converge to 5x. But if not, then it may fail to converge at certain points. Okay. Now, here's something to point out that can be a time saver on a test. If I give you a problem like this and say, solve it by separation of variables, and if you know that because of the boundary conditions, your solution will be a combination of these functions, sine n pi x, and if 5x already is given to you as a linear combination of these functions, then you don't have to compute this integral. You can get your coefficients an just from, you can read it off the linear combination. Now we will see examples of that later on. I just want to point out that there are certain problems where to get these coefficients, you got to evaluate an integral and it requires something nasty like integration by parts. And there are other cases where you can just read them off your initial data. So it takes no time at all. I also want to point out that the solution has decaying exponentials. So these exponentials go to 0 pretty rapidly as t increases, especially for larger values of n. That would go to 0 really fast. But it tends to make a solution smooth. So that's a property of solutions of the heat equation. They're known to be smooth. So what that means is, if you just simply take the first term, this one, that's actually a pretty decent approximation, especially for larger values of t. So you get so even though we have a solution that's an infinite sum, at least it's approximated by a much simpler expression. Okay, this I mentioned earlier. Because it's Dirichlet boundary conditions, u being 0 in the boundary, that's how we know that it's a combination of sine functions. If it's du dx equals 0 in the boundary, then a lot of the manipulations would be the same, but it would be involving cosines instead of sines. And integrals involving cosines also satisfy equations such as this. So both sines and cosines have that orthogonality property. So to summarize, to solve a PDE such as this one by separation of variables, first, you assume a solution has this form, product of a function of x and a function of t, substitute it into the PDE, and then put all parts of the expression involving t on one side and anything involving x on the other side. That, in other words, function of x equals function of t. Then you can equate both of them to a constant. That is what gives you the ODEs, one for x, one for t. As far as the constant is concerned, check. Cases where the constant is 0, positive, negative, see which ones have a chance of satisfying the boundary conditions. But it tends to work out this way, but it has to be negative. And based on that, you solve the ODE. Most cases, it will be an expression such as this, a combination of a sine and a cosine, because that's what you need to satisfy the boundary conditions. Then you solve the ODE in t, enforce the boundary conditions, so now the PDE and boundary conditions are taken into account, and then we satisfy the initial condition by expressing our solution as some kind of series, where returns in the series involve the solutions of both ODEs, the ODE in t and the ODE in x. Now, we will be seeing plenty more examples of this in coming classes, but this is the illustration of a general procedure. So PDE, the boundary conditions, then initial conditions. Okay. Are there questions? Are there homework questions?
Lesson 2, number 1.
Okay. I need to share so I can have a book up. No, I don't want WebEx Assistant. I said no. Hold on. Okay, lesson 2, number 1.
Yeah.
Okay. Apparently my director is in catch-up on emails mode. Okay. All right, so for this, this goes back to a comment I made last time about the heat equation, that how the temperature changes, whether it increases or decreases, depends on the concavity of the solution. So for instance, if the what happens if the solution is concave up or concave down, therefore uxx being positive or negative, and how that will affect the temperature. And so based on how this function behaves, if you were to see a graph of it on the interval 0 to 1, and you can see its concavity, then you can have an idea of what's going to happen to the temperature.
Are we supposed to use the formula like alpha squared times 2 over delta x squared?
Oh,
that one or not?
That's not necessary.
Okay.
Yeah, because I'm not looking for you to, basically, all I'm looking for is the temperature going to increase or decrease?
Okay, I thought we had to find like u of x at t or something.
No, because that's what I covered today.
Yeah, I was confused about what we were
Now,
looking for.
After what I've shown you today, this problem can be solved, but we're not dealing with that in this problem.
So you're just asking for the concavity at 0 and 1?
Yeah, in other words, and what that means from a temperature.
Okay.
Yeah, will the temperature increase or decrease as time moves forward? So there you want to know, is du dt positive or negative in this case? Other questions?
So define concavity, we just integrate it with respect to t, or I mean to x?
Define concavity?
No, like to find concavity, do we need to integrate it, or?
No, because the concavity is determined by the second derivative, so you're just going to take the second derivative of this.
Oh.
Actually, you don't even need to do that. If you were to see a graph of this, that also would tell you concavity. Yeah. There's not much to this problem.
So with that one, oh never mind. I was about to say the answer, but it's just
Okay.
So I'll put it on the homework.
Okay. Thank you. One thing I should add to the notes, because we saw a few ODEs, and when those came up, I just jumped to the solution. So I want to review those because there may be some rustiness from like Math 285 or whatever your ODE class was. Okay. So the ODE in time, well, it's first order, and then the ODE in space, the second order. Okay. Actually, both were linear, so let's limit ourselves to that. So here's the solution formulas that I used. So the ODE is t prime is equal to some constant times t. Oh, actually, I'll do two cases here. So, actually, I'll use k here. Is equal to its initial value, whatever it may be, times e to the kt. That's what I was using to solve for the ODE in time. That's where exponential came about. Now, how you would get that? Use the fact that this ODE is called separable. That might ring a bell. Where if you think this is d capital T, d little t is equal to k capital T, and you rearrange it so that you have capital T on one side, little t on the other. Integrate both sides with respect to the respective variables. That's how you solve the separable equation in general. And then this solution is what pops out. Now, if I modify this a little bit, you probably go to kt plus some function that I'll call b of t. Now, we didn't need this here, but it will be needed some other time. So what's going to happen is you're going to have the same term at first, but then because of this b of t here, there will be an additional term. Whoops. A, S, S, yes. And the way you get that is using what's called an integrating factor. In this case, the integrating factor would be e to the minus kt. So, so that'd be the idea that you have rustiness when it comes to ODEs. To you still have your own materials, but here it would be. But I'm really fine if you jump into these solution formulas whenever ODEs like this come up. So certainly this one will be used quite often. Now, for solving the ODE in space, second order 3 ODEs came up. So general second order ODE has this solution. Okay, actually, what you do is you solve a quadratic equation. That comes from the ODE. So if think of order of differentiation corresponds to power of lambda squared plus p lambda plus q. And the quadratic equation, it'll have 2 roots, r1, actually I'll call lambda 1, lambda 2. Now, the format the solution has depends on the 2 roots. So first case, and this came up when we're looking at the constant k being positive. Okay. So the roots are not equal, and they're real. then the solution is, all right, so then we have some constant as an exponential, the root R1, and another constant, and an exponential involving the other root, R2. So it has that form. So distinct real roots get exponential. If the roots are equal, so discriminant is 0, it's similar, but because R1 and R2 equal, these terms need to be linearly independent. The other term would be x, like a constant times x e to the R1x. And finally, if the roots are complex, so form alpha plus I beta, or I should say plus or minus, because the coefficients p and q are assumed to be real. So the roots, if they're complex, they must be complex conjugates of each other. So then the solution has this form, constant times e to the real part times cosine plus our constants e to the real part times x times sine. Right, so that's what solution can be in these cases. So the first and last ones came up today. This came from a case where k is assumed positive, and here where it's assumed negative. Actually, this case came up as well, where you have roots R1 and R2 assumed to both be 0. So then you have a constant plus another constant times x. So that's your Crash Course 285 review. Okay. Still a good amount of time or questions.
So the first order linear ODEs would you use for step 1 or in step 1?
Actually, okay, that's my steps here. Well, if you come across both ODEs in both orders, like second order for x, first order for time. As far as where you actually solve that, oh, okay, that's toward the end of step 1.
Yeah.
Yeah, step 1's a pretty large step. So, yeah. Yeah, so that's where you come with both ODEs and solve them. Okay. Because there's enough time, I'm going to do another example. Now, this is kind of risky because I'm just making this up right now. We'll see how it goes. So the problem we'll solve is again the heat equation. I'll fill in a number for alpha squared, so 4. And I'll choose a different domain, x going from 0 to pi. This for something different from the previous one. The boundary conditions, I'll set the derivative, first derivative equals 0. Oh, that's fine, that's 0t and pi t. And then the initial condition, cosine x minus cosine 4x. Okay, so that's our problem. Now, all right, so we're going to assume that solution has this form. Some now I've started to sum from 0 to go off to infinity, whereas I used 1 before. I really could use either 1. It's going to turn out to be more convenient, and you'll see why. It has something to do with the boundary conditions. So we assume u and of t as a product of a function of x. And satisfies E boundary conditions. Okay. So then we substitute that function u of t into P. So now we have derivative of this with respect to time. We'll leave xn alone, but we differentiate the time part. And then on the right side, there's the 4 there, and then we differentiate the x part twice, and then leave the t part alone. Then we rearrange. Everything x on one side, everything t on another side. So we have a tn prime another way to think of it is divide both sides by x, xn, and tn. Yeah, really that's the easier way to come up with it. Okay. So we have tn prime over 4tn. And then we have all the x stuff. Okay. And because of time, I'm going to, I set both these equal to a constant, which is function t equals function of x. What will happen is if you were to assume that the constant could be 0 or positive, they'll turn out not, well, actually, I do need to be more careful about that. Okay. Okay. So, if you have done in 3 cases. K equals 0. Then we have xn double prime equals 0. So the solution is an plus en x. So it's a linear function of x, as we saw last time. But now you want to make sure that satisfies boundary conditions, but the boundary conditions are different. The boundary conditions are x n prime of 0 is 0, and x n prime of pi is equal to 0. What's the derivative of this? The derivative is going to be the constant bn. So that constant has to be 0. So this time we can have a non-trivial solution, a constant function. So that's the difference because of the boundary conditions. Because we're not requiring this to be 0 at 2 points, we're requiring its derivative to be 0 at 2 points. All right, so k equals 0 is not ruled out this time. K is positive. So we have xn double prime minus kx n equals 0. So the general solution, yeah, the other was also a general solution. So that's a constant e to the kx plus constant e to the minus square root kx. Now, I'll have to gloss over this because of time, but it'll turn out that this won't work. It plays out similar to a case of Dirichlet boundary conditions, where you set up a system of equations, derivative being equal to 0 at x equals 0 and x equals pi, they'll only have a trivial solution. Why is everybody leaving the meeting?
My laptop ran out of battery earlier, so.
Okay. Other students were leaving. It's like, I'm not done yet. I see that I'm almost out of time, but still. Now, k is negative. I'll assume it's equal to minus lambda squared. Then we have the general solution is x is equal to constant cosine lambda x plus sine lambda x. So now we have to check what it'll take for this to satisfy the boundary conditions. Okay. So to satisfy them, we need xn prime of 0. So if we take a derivative of this, we're going to get minus lambda an sine lambda x. Okay, so take a derivative function of x. Plus lambda bn cosine lambda x. So that's a derivative in general. Now we substitute in x equals 0. Well, sine of 0 is 0, and cosine of 0 is 1. Okay. So what happens in this case is that our lambda equals 0, Bn equals 0. Why are people still leaving? I get a notification when someone leaves the meeting, and it's aggravating. Okay. I better still be recording. Okay. All right. So in other words, there's not going to be a sine term. And actually, if lambda was 0, again, that term is 0. Then we look at the other equation. Okay, so xn prime of pi and we know that one way or another this term has gone away. Okay. So same thing before. Lambda has to be, so this angle has to be an integer multiple of pi, but there's already a pi in there. So okay. So either k is equal to minus lambda squared, where lambda is an integer, and as same reasoning as before, we took positive integers, so nothing's redundant. Or k is 0. So again, so really k is equal to minus lambda squared, where our conclusion for the spatial ODE is that we have n cosine okay, n x non-negative integer, because earlier we concluded that xn being a constant function is okay. If n is 0, then it is a constant function. So that covers everything that could possibly work. So these are our non-trivial solutions. Looks like I really am out of time. So we're only, yeah, okay, now clock just struck 3:45. I'll have to continue this on Monday with the solving the time part and then bringing it all together to this solution. Okay. I'll stick around in case anybody has any questions, but I've stopped recording at this point.
Is your homework